Welcome to everyone who's currently joining. We're going to wait a few minutes until we start, so just arrive here in this room. Welcome to everyone who's joined already. Okay, so maybe let's start. It's possible that still participants might be joining, but that's not a problem. Welcome to the webinar of the NiChe cluster. My name is Annika Schmidt-Peter and I'm a communication manager of the Simplify project. The acronym NiChe stands for Using Non-Conventional Energy Sources for Feedstock Material Processing. And this is the common topic of over 4 EU projects that form the NiChe cluster: Destiny, Perform, Simplify, and Liberate. Today you can get to know 3 of these projects, namely Destiny, Perform, Simplify, Perform, and Destiny. You will see today, you will today get some insight into these 3 projects, and you can also ask your questions in a Q&A session. If you have any questions, we will have the Q&A session at the end of this webinar. Please write all your questions into the chat, and you can also indicate who you want to address with your questions. Maybe these are people from specific projects or all people who are present. Just indicate that, and we will delegate your questions to the relevant people. As you can see in the agenda, we also have a short introductory speech by a representative from Aspire, Evelina. And I would, without further ado, give over to Evelina, who will introduce the NiChe cluster and this webinar. Thank you for your upcoming short presentation.
Good morning, everybody, and thank you very much, Annika. Just give me one moment to share my presentation. I hope it's showing fine. So my name is Evelina Ponks-Nite. I work as operations manager at Aspire Association, and I'm really pleased to join this webinar today of several Aspire projects. I will briefly talk about Aspire and the new processes for Planet Partnership. So let me start with presenting here. Sorry, I see the GoToWebinar software. I need to close it somehow so I can follow my own presentation. Sorry for this. So Aspire was created in 2012. It's an association of process industries. We have recently celebrated the 10th anniversary of the association. Aspire represents more than 180 different stakeholders, so different members from research, from industry, different size, large and small, also some innovation agencies and other type of members. So Aspire was created in 2012 with the purpose of managing the first public-private partnership for the process industries, which was called Aspire PPP. Aspire PPP was implemented under Horizon 2020, and the projects that are presenting today, they resulted from this Aspire partnership. Now, since Horizon 2020 has ended, we have also transitioned into the next partnership, which is called Processes for Planet Co-Programmed Partnership. This partnership is implemented in Horizon Europe. It's linked to the Cluster 4 of Horizon Europe, but also has links to connections. It has links in Cluster 5. We do say that the Processes for Planet is a successor of the Spire partnership. Nevertheless, it has a way broader scope. So in the first place, we have grown from 8 sectors, which we had during Spire, to 10 sectors, with refining and pulp and paper joining association in the recent years. Besides, this partnership is broader in its ambitions and also in the funding that is being allocated to Processes for Planet projects. So in the course of Horizon Europe, we are going to have 1.3 billion euros allocated exclusively to Processes for Planet projects, which is nearly 30% more than we had for Spire projects in Horizon 2020. In I think 2017 or 2018, at around the time when your projects were funded, all the stakeholders, all the partners in Inspire came together to also see, so what is next for process industries? What should we do after Spire? What are the challenges that we have? And of course, that challenges are the high impact on climate, the linear use of resources, also the need of remaining competitive, and the need for de-risking the new innovations. So then we came up with the Spire 2050 vision, which defined 3 main ambitions. And the first ambition is the climate ambition to address climate neutrality. The second one is the circularity. So it's about addressing the circularity aspects and competitiveness that would allow growth of process industries, which is quicker than EU GDP. So with these 3 ambitions, we then moved further into developing the strategic research and innovation agenda. So how will we achieve these ambitions, these very ambitious targets? In the period of 2014 to 2020, the Spire PPP's project have been developed with very high and very positive impact. So with the reference to the resource and energy efficiency, we see the excellent outcomes that have been achieved here in terms of environmental KPIs, jobs, the significant innovations that of course contribute to all the areas, also competitiveness, participation of Spire SMEs in projects, and of course the leverage, which was more than 8 by 2018, 2019. When this progress monitoring report was done, the projects that are presented today, they were just about to start or just have started. So their contribution is not included yet in these numbers. However, we see the great potential and the high impact already in the first 4 years with the first project. And the contribution of projects that are presenting today is, of course, very significant, with also contributing to the energy efficiency improvement, resource efficiency improvements, as well as reduction in CO2 emissions, decreasing the CAPEX and OPEX, and so on. So this is definitely contributing to the KPIs of Aspire, and it's building further on to Processes for Planet, helping to achieve its objectives. Now, when developing the strategic research and innovation agenda, we looked at what are the enablers, and we defined 4, which you can see here on the left. And these are industrial urban symbiosis, digitalization, non-technological aspects, and the process innovation, which is done detailed in electrification, energy mix, CCU, the resources, efficiency and flexibility, and so on. Together with these enablers, we have also defined 14 innovation areas, which you can see on the right. And these are the main areas that at that time we consider as being the main areas that the process industry needs to address in order to achieve its climate neutrality and circularity objectives. As you can see, the most relevant in terms of the scope are the renewable energy integration, electrification, electrically driven processes, and so on. However, we know that there is no silver bullet, so there will not be one innovation that will get us there. And what we are looking at is actually a combination, so a mix, or what we call a tapestry of different innovations to achieve climate neutrality. So on the energy side, the innovation is needed to change the energy mix through new technologies for the integration of electricity, energy efficiency. Also, the waste energy reuse will be playing a significant role. So we put all these areas that we identify as important contributors into the innovation areas, innovation programs of the Processes for Planet 3. So now if we put this all together, Aspire is a unique cross-sectorial community, and projects that have contributed to Aspire are of course part of it. Their innovations and their advancements are very important there. Then we have the Processes for Planet 3, which defines innovations that are needed to move forward. On top of that, we have defined 2 initiatives. The first one is first of a kind plants, and the second one is hubs for circularity. I will not elaborate on them today. And with this, we are aiming at achieving impact and climate neutrality, near zero landfilling, near zero water discharge, and competitive EU process industry. So with this, I finish, and I want to thank you for giving this opportunity to briefly introduce Aspire and Processes for Planet. And I would like to hand over to the project so that they speak about their innovations and about their achievements in more detail, because they are a very important part of bringing process industry closer to its climate neutrality, circularity, and competitiveness goals. So thank you very much.
Thank you, Evelina, for giving this short insight into this research innovation community of Aspire and showing us some really impressive numbers and insights on the impact. I would like to give over to one of the projects of today's meeting, which is Perform. So Erwin, I would like you to share your screen if it works, and then I'm excited to see what you want to present to us.
Can you see my screen?
Yes, we can.
Okay, so let's start. Thank you for this opportunity to present the Perform project. My name is Erwin Gieling. I'm the coordinator of Perform. I'm a project manager at TNO in Delft, working in the Voltegem program. So today we'll give you a brief overview of the project and also its main recent achievements. The project already runs for some time. It will run for 4.5 years. It started in January 2019, and we have an extension due to COVID until June 2023. The overall objectives of the projects are to develop and construct a versatile modular Tyrol 5.6 electrochemical power platform. And with that, we aim to valorize bio-based materials into chemicals, and it will be an open access platform. After the project, it will be available for companies and research institutes to continue the research and scale it up further. So we will demonstrate on this power platform 2 showcases, and with different feedstocks at variable throughputs. And of course, an important part is to disseminate and exploit the results that we obtain in the project. So why are we doing this? Well, the project targets the 2 global trends already touched upon in the introduction. One is, of course, the energy transition, electrification. Processes should move from fossil fuel-based to electric energy use. And secondly, the shift to bio-based feedstocks. So that is about circularity, and all related, of course, to the Paris Agreement and the Green Deals and a couple of other objectives of the European Union. So the project concept is based around an electrolyzer, an electrolysis process where you use electricity to convert feedstocks. And in this case, we're using renewable feedstocks from biomass, and in particular, second generation biomass that is not in competition with the food chain. We use renewable power, and we produce high value chemicals that could be new chemicals or plug-in chemicals for the processes. The project is built upon different phases, and it is based on the feedstock platform analysis, where we started with analyzing the sugars and the feedstocks that we can use for the electrochemical conversions. Platform innovations, so we design on smaller scale the platform, and we scale it up and integrate it and demonstrate it, and in the end it's about exploitation of the results. I come back to that later. Key innovations in a project is that we want to do paired electrosynthesis. So in an electrolyzer you have an anode and a cathode side. We want to utilize both sides, which is far more efficient than using only one side. The upscaling of novel electrodes, electrochemical process intensification, that's about integration, that's about demonstrating the whole chain, and it's also about the system design as a whole for scale up. So we have two showcases. One showcase is about a paired electrosynthesis, and as an input there we use furfural and livalinic acid, and we will produce maleic acid and valeric acid. The other showcase is a tandem electrosynthesis, where we go from glucose via glucaric acid and oxidation, and then we hydrogenate to adipic acid. Applications of these products are polymers, plastics, lubricants, and you also find applications in perfumes and cosmetics. So this is backed up by our industrial partners, Novamont, Radici Group, and Perstorp, who will do the product assessment of what we get out of the demonstration and test if the products are fit for their applications. We have a strong international consortium, 11 partners, 7 countries along the whole development chain. So from electrochemical system and catalyst experts, research institutes, reactor development, system integration, until exploitation and commercialization, with companies and universities from throughout the whole of Europe. Expected impact is described as the main KPIs that we defined as one electrochemical pilot. That is a big objective deliverable of the project, because it will remain and will be open access infrastructure. We aim for energy efficiency, increase energy efficiency compared to non-coupled electrochemical processes, because we're doing two things at the same time. We will develop electrocatalyst electrodes with a high faradic efficiency again, and a low overpotential, which means less losses in your process for the selective oxidations. And the aim is to demonstrate this performance at TRL 5 with selectivity of 80%. Important part of these electrochemical conversion systems is the downstream processing. I will come back to that later, because actually you need more units for processing than for the conversion itself. Techno-economics and benchmarking is always very important to show that you can scale it up in a commercial beneficial way, that you will have a business case, and also with respect to the decrease in CO2 emissions that you expect. Then dissemination, communication, exploitation, already mentioned, very important. This is the timeline of the project. We started in 2019 with the analysis and the innovation, and also testing at a surface area of the electrodes in your electrolyzer between 1 and 100 square centimeters. Then in 2021, we reached already 1,000 square centimeters as a demonstration in the lab. Then the aim was this year to finish the whole project with 1 square meter electrode area and a production rate of about 250 grams per hour. That didn't work because there's a lot of problems in the logistic chain and materials and components that you just cannot order at the moment, with long delays again. And the pilot will be now ready. All the equipment will be ready end of the year. So we will be testing in the first half of 2023. Hopefully, just before the end of the project, we will get the great results that we aim for. So some project highlights. Where are we? What have we done? Well, the feedstock has been analyzed, and we established a process to in the Power Platform. So we started with reaction and catalyst development. So there will be new materials and new catalysts in the Power Platform. Then we went to reactor and process development. This is the 1000 centimeter square reactor that we tested, developed by EasyTech and tested by TNO. From all this data, we could go to a process design for the full-scale stack plant that's currently being built. It's similar to this one, and it's about container size, and it will go to 1 square meter of reactor stack to 250 grams per hour. Well, this is not it, because you need a lot of steps beside the electrochemical conversion plant, and that's called the downstream processing. So what do you need? You need to recycle your electrolytes, you need to purify your streams, you need to extract your products. So we need a rather large electrodialysis setup to get the salts out again and for the recycle of your electrolytes. Then we have different units like concentration, crystallization, filtration, liquid extraction, and distillation. And we don't use everything for all the routes, but these are the setups that are now available in a modular way, and we all connect them together in one system. And in the end, then you arrive at your target product. In this case, what I show you here is maleic acid. So to be a bit more specific, what we've been doing in the lab, we already showed this at 1000 centimeters square. Here is the reactor again. So the showcase here, we go from furfural to maleic acid. It's an oxidation in a 1000 centimeter square reactor, and we use a 5-liter crystallizer. So we synthesize with a yield of 80% of 5-HFO, which is an intermediate to maleic acid, a conversion rate of 99%, and a ferritic efficiency total of 70%. Then we did a separation process from the reaction mixture, and we used pre-concentration following by cooling crystallization, filtration, washing, and drying. So that is the chain depicted here. And we reached a separation yield of 85%, purity of larger than 95%, already very close to the targets and the KPIs that we set ourselves. We saw some colorization, so there is still some degradation products in there. And also there is some sulfuric acid still in there, which is the salt that we use for conductivity in the electrolyte, and it should be taken out, of course, in the product. And there's also 1% of 5-HFO present still in the end product, and that can still be optimized in the final setup. So here you see how the product looks like in small scale. So we can already do tens to hundreds of grams of product with this setup. And then, of course, we have to go to the full scale demonstration next year, and after that, we will have a lot of data gathered, and we can go to the process assessment and life cycle assessment, which is an important part of the project. And we also can do optimization and scale up of the technology to have a development plan beyond the Perform project. What can we do with the platform? What can we do with the demonstration cases? And also, how can we maybe have different demonstration cases on the platform? And the process assessment also comprises of application testing that we're doing by the industrial partners. So this is a task in the project, and then another task is the business case analysis, where of course we have to show, or hopefully can show, that we already have attractive business cases And the preliminary TA based on the laboratory data that I just showed you indeed shows potential positive business cases if we reach indeed the target performances. And for some of these products, we're already really close to that. And finally, dissemination, communication, exploitation, capacity building is very important. With this respect, I'm very happy to be able to present that in this workshop. Please visit the Perform website. There's more information there, and also free downloadable reports. We have quite some achievements over the last years already. A lot of KPIs that we have here already met, and we're also very happy to cooperate with Destiny, LIBERATE, and Simplify projects, and we make use of the Horizon Results Booster to further disseminate and exploit our results. So, summary, demonstrated electrochemical conversion and integrated this DSP already at lab scale. We are busy with finishing the Perform platform pilot. It's under construction for the conversion of bio-based feedstocks to maleic, valeric, glucaric, and adipic acids. It comprises of a flexible electrochemical reactor stack and a modular and integrated DSP. Everything is kit-based, it's open access, it will be available after the project for research parties and industry. And then finally, we hope that we can get the full demonstration of the Power Platform and do a product quality assessment in 2023. So that was it. Thank you for your attention.
Thanks to you, Erwin, for presenting the Perform innovations and research so far. A reminder for everyone who's joining today, if you have any questions, just write them into the chat, and then we will talk about any questions at the end of the presentations from each project. The next project we're going to hear something from is Destiny. And so I would ask Angel to share screen and show us what has been happening in Destiny so far.
Yeah, now, thank you. I will try to share my screen. I think you should see. It is okay?
Yes, yes, it's
okay.
Working.
Excellent, excellent, thank you. All right, so yeah, okay, Destiny project is the approach we made to make the electrification in intensive energy processes. So Destiny's development of efficiency microwave system for material transformation in energy intensive process for an improved yield. My name is Angel Lopez, and from CIMAT, so I am scientific coordinator of the project. Okay, this is the summary that we will speak about. The Destiny is a European project inside the SPIRE context, as you can see. And we are using microwave as energy alternative to the gas or to the fossil fuels we are doing now. And later we will see the scale-up technology we are doing or how it's developing at the moment. So inside the context of SPIRE, we are covering, or we try to cover three main things: electrification of industrial process using microwave technology. Not any other kind of energy sources is involved in this, so only microwave technology for all the process. And efficiency and flexibility, we are using the primary resources or maximizing the use of primary resources, for example, for using local clays for cement, instead to have long transport. Also the recycling, using, for example, iron bearing residues from the steel industry, and maximizing the recovery of sensible heat using cool kilns. So this is the thing we are doing now. So in the context, unfortunately, you know too well. Also, sorry, for that is the key issue in Europe is to go to reduce the emission, CO2 emission, and then the electrification is one of them, and the microwave is the technology we solve or we use for many reasons, mainly because it's the probably the more efficient at the moment to do that. So in the context, this is unfortunately, is so the price of the electricity now is growing up too fast, and the geopolitical question is, of course, is pushing too much, and then this is make also the opportunity to encourage assisting or try to change the industry in Europe. Okay, the general overview of the Destiny is try to do the high temperature microwave processing using a first of a kind system for 3 materials in 3 sectors: cement, ceramic, and steel. In cement industry, using calcined clays, using for pozzolan, so to substitute 30% of the material, the clinker, by this material. In ceramic is to perform pigments. The conventional are also new colors, so is new technology. Then you can use new formulation, new color, new pigment. And in the steel sector for iron binding, that is quite relevant to save these bioproducts. So to convert the residues in bioproducts. Okay, the concept and challenge is to make a microwave system knowing better the interaction between microwave and material, even to create a new science or a science and technology involved in this in the system. For example, determining the electric properties in continuous, and to implement this in the system. The microwave applicator design able to process in high volume and high temperature for this kind of product. The third point is the monitoring and control strategies, because it's new system, you need monitoring different ways, so you have a different problem that appear, and then so you need to consider the system in different way that is than conventional, that is more longer life existing. So you can see there are many implementations, so we need to solve this one also for microwave. And the fourth point is the consistent engineering over the whole life cycle, and implementing the KPI, so determining the KPI to demonstrate how the Destiny cover the target that should be covered. Okay, the general so the consortia is doing by 15 partners. There are large enterprise, SMEs, consultancy companies, research, technology provider, industrials. So more or less covering the Europe. So some countries are not, but indirectly they are also involved. Concept and challenge is to make a first of a kind system, and starting from raw materials, so from feedstock. So there are some partners quite expert in that. So they had the problem, the industrial, the teams that can afford the microwave kiln system, and cover all the other system to have the final product. And in this case will be pigment, calcined clays, and pig iron and zinc, as you can see here. So the methodology for implementation is just from lab scale integration and demo. Now we are in the last case, and then the other work packages are all running to cover all the system. Now we are in the last step of demonstration. So the idea was to develop a modular system, modular plant, based in the microwave kiln that later you can replicate to have a array of kiln cells that we call to cover the production. So you can just add elements to create a huge plant or something like that. So in the pilot is based in microwave kiln module, and the other is the module of feeder, and so the feedstock. And in this case, we decide to do into different plants. One specifically for steel because it's more different, and the other with cement and ceramic that there are some more similarities in the system. So this is the pilot plan as designed. So in the bottom, in this case, we put in the bottom the microwave kiln or microwave system, and in the top, just the feedstock to be easy integration. The other, okay, this is the inside. How is the thing inside? You can see here the feedstock part and the microwave part, and here how is implemented now. We put an office outside just for the noisy and everything, so you can control. And here you can see how is from the control panel how to check the production. So this is the feeding system. So from the raw material feeder, all pneumatic, so it's quite fast. So we are using the fast system, and to final deposit storage. Considering also the cooling system. So cooling system that because it's pneumatic is easier and have some advantages and faster for the system. For the microwave, have fortunately very fast resident time. So the resident time is very short. So the material can be going faster than the conventional. So the system, yes, is some technical things. Yes, how is the kiln? I will pass through soon. So this is the modeling. Just some screenshots just to see how is the aspect of the material growing through the reactor, we can say, and of course everything is modeled before and later just to correct the things, so the change. And this is the comparison between the conventional and Destiny, so and microwave kiln, just to see how is the difference and the main different one each other. I can see just few words about in the conventional in this kind of kiln is in large production, so thousands of tons per hour, and this is not suitable for downscale, and with microwave is suitable for downscale, and so for some flexibility production is much better, and some have other advantages. Okay, other relevant thing is the long start period that you need for the conventional system, and the microwave is switch and go. So it's quite fast to put, and you don't need preheating or changing things. So it's quite simple from this point of view. It's difficult to put in to create it, but later it's quite robust. Okay, other relevant things is the gases. So in the microwave you can recover the gases because it's only gases of reaction. So there are not CO2 contribution, there are not combustion gases, just the gases of the reaction that then you can use for other things. Okay, this is the design from the, just to see from the design of the simulation to the performance. You can see here some point, how is, so we are, is a point red because we are working more than 1000 degrees. So we are up of this temperature. and then okay have but the system is always metal, so, and it's quite cool, so they are not overheated outside. A monitoring system, of course, is quite okay. You can control by local screen, and to also from the beginning, because due to COVID, also we put a remote interface just for the colleagues. They can take some samples, some inputs, some results from the beginning, and now it's very useful to work in remote. So we have you can operate in local and work in analyze the result in remote. So some detail of the data we collect. This is a system. How is the temperature? The real temperature is the blue one, for example, and this is in brown is the orange. Is the simulation you can obtain with the soft sensor that is a team doing. So some example. In cement sector is calcareous clays. We obtained we had around 600 degrees perfect target to also perfect results. More than that was useless, was not needed. And so the conclusion we can say from this product, it is or the advantage is that with Destiny 600 degrees is good enough, and resident time is less than 2 minutes. In compared with the conventional that is 800 or 850, with resident time of around 2 hours. This is the conventional compared with the actual. So with the Destiny. In a steel sector is there are some we can perform the process in a single step, just to separate also the metal, to have the reaction and the separate the metal. And the temperature is as expected, so not a big difference with this. And the resident time was 6 minutes compared with the conventional that was needed two steps, and each one was more than 120 minutes. So there are really improved in time. In ceramic sector, this is the process. So advances in the project to have the process material. So in this case, is a blue pigment. Then in Destiny, the resident time was 4 minutes. Temperature is not reduced, so it's more or less similar to the conventional, but in resident time is quite significant change. So, and this is for my side. Thank you very much for this opportunity. So for my side, thank you.
Thank you for presenting, for giving some insight into the Destiny project, NiChe.
Thank you.
I would like to go to the next presentation from Tom, who will show what has been happening in Simplify, and then at the end we can come to the questions. So write your questions into the chat so we can come to all the questions afterwards.
Okay, I guess you can see my screen and you can hear me?
Yes.
Okay, very good. So thank you very much for, just a second, trying to get this moved here. And now it's gone, of course, my screen. Yeah, okay, good. So welcome everyone from my side. My name is Tom van Gerven. I'm from the University of Leuven, and I'm the coordinator of the third project that is being presented here, which is Simplify. Some general info that I want to share with you, similar to the previous projects, we're funded by the same call in the Horizon 2020. program. So the call was the Spire call on processing of materials feedstock using non-conventional energy sources. Originally a 4 years project. We started in November 2018, but due to the COVID-19 pandemic, we were extended, or the project was extended for another 6 months. So we will finish by the end of April 2023. So that's still more or less 6 months left that we're in the project. So Simplify stands for sonication and microwave processing of material feedstock. So it immediately shows that we are looking at 2 types of alternative energy forms, ultrasound and, similar to the previous project, also microwaves. And the project tries to move from a technology readiness level from 4, which is basically technology validated in the lab, to a TRL level of 6, where we can demonstrate an industrial system prototype. So for us, the motivation was the following: the fact that we see in many chemical industries still a tendency to have batch production, or at least tank production. Often there is either batch or CSTRs being used, which, if you look at the right-hand side in the picture, this is very much like we have been doing for many centuries. We're relying on mechanical mixing, we're relying on conduction and convection for heat transfer, which means that our transport phenomena in these chemical processes, heat transfer, mass transfer, momentum transfer, are not ideal, not optimal. In addition, we often have limited process control in these large tanks, which leads to, in the end, a low resource efficiency. So we have the vision to move to intensified processes by moving from tank reactors to continuous flow reactors. With that, we hope to be able to come to a more precise process control, leading to higher resource efficiency. Now, this is a transition that has been going on for many, let's say, years, even decades already. But what we do see is that the transition is difficult for, let's say, the more multi-phase streams. And we're particularly looking at 2 of these types of multi-phase streams, streams that contain solids in a liquid, and viscous phase streams, so polymerization processes. Our perspective is that we're using these alternative energy forms, and in our case, ultrasound and microwaves, to act as enablers for the transition from tank production to reaction flow, particularly for these difficult multi-phase streams. And of course, in addition, and this was also mentioned in the project call, and we also have taken it up in our project as well, this electricity, or the electrified sources like ultrasound and microwave, might derive their electricity from renewable sources more and more in the future. And this is also something that needs to be taken into account. The consortium that we have consists of 11, 12 partners. We have end users. We have basically 3 chemical companies. We have Coatex, which is based in Lyon, which is a polymer company producing polyurethanes. We have Arkema, also a French company based in Paris, but the affiliation that we work with is located in Pau. And then we have the Italian company of Colorobia, which is located near Florence. I'll come back to their case studies in a minute. Not only the case studies, or not only the end users we have in the project, obviously we also have universities, research institutes. I already mentioned University of Leuven in Belgium, but we also have Dortmund University in Germany. We have the Fraunhofer Institute, one of the Fraunhofer Institutes, the Institute of Chemical Technology, also in Germany. We have the university in Modena in Italy, and we have the National Technical University of Athens in Greece. Then we have 2 technology suppliers, Weber Ultrasonics, dealing with ultrasound energy, and Mügge, dealing with the microwave energy. Both companies are German-based companies. And then we also have two service providers, Quantis and Dinergy. Quantis is a Swiss-based company, Dinergy a French-based company, and they are dealing with exploitation, with valorization, and also with life cycle assessment and evaluation of carbon dioxide emissions. So what are the processes in focus? So as I said before, we're looking at processes with difficult multi-phase streams. All of them are based in the specialty chemicals industry, and we are trying to look at the transition from batch or tank processing to continuous processing. And as I said before, we're looking at two types of energy forms, ultrasound and microwave. More in particular, we have three use cases, and each of these use cases refers to one of the three end users, Coatex, Arkema, and Colorobia. We have the first one, which is the polymerization work, the highly viscous streams, difficult to process in continuous reactors. So we're looking at those ones. There we have reactive extrusion as technology of choice, as the continuous technology of choice, and we're dealing with polyurethanes. And as I said before, the Coatex company is the end user for that. And we're trying to combine reactive extrusion with microwaves and ultrasound. Secondly, we have, and thirdly, we have two processes that are dealing with suspensions, highly loaded suspensions. And the first one is suspensions that have long residence times. We're talking about many hours. And for that case, we have a zeolite synthesis, reactive crystallization case that we've chosen, and we're using as continuous technology, we're using a continuous oscillatory baffle flow reactor, COBR in short, that we're combining again with ultrasound and microwave. And then the third class of chemical process is that of, again, involving suspensions, but now very quick reaction rates. We're looking at a reactive precipitation reaction, nanotitania production in a plug flow reactor. And again, application of microwaves and ultrasound is relevant for this plug flow reactor for nanotitania synthesis. And this is the Colorobia case. The previous one was the Arkema case. Okay, so how do we approach this problem or these cases? As I said, we have basically reactive extrusion, one case study. We have two case studies in the reactive crystallization or reactive precipitation. So you see here the polyurethane with Coatex, the zeolite synthesis with Arkema, and then the titania or nanotitania synthesis with Colorobia. We're looking at two types of alternative energy sources, microwaves and ultrasound. And very important is the process control that we also have to make sure that works, not only from the perspective of these new energy forms, but also from the perspective of the fact that we're trying to work with renewable energy, so renewable electricity, which also comes with a certain supply, temporal supply at certain time spaces, and this needs to be integrated in the process control system as well. Obviously, we have the supporting work, dissemination, communication and management, technology transfer, and the life cycle assessment also in place of the project. In terms of results, so we kind of looked at or approached the project as follows. So we started in two parallel tracks. First, we did, or one parallel track in the beginning of the project was that we've done a parametric study of microwaves, of ultrasound, and of process control strategies for the different use cases. That's work that is mostly done at the university sites and the research institute sites. And then the second track is that we already started from the very start of the project with the transition of the batch or tank systems to a flow system. not yet involving the microwaves and the ultrasound, but already moving to a continuous flow system, which was first validated and then demonstrated. In the meantime, we had microwaves and ultrasound and process control of flow systems being investigated in the parametric study, leading to, in a second stage then in the project, to enable us to go to a validation of the flow system, incorporating now the microwaves and the ultrasound, and then later on, which is basically where we're now, demonstrating the flow system that is involving already the microwaves and the ultrasound, and also the integrated process control. So as I said before, we're now in the last, or we're entering the last 6 months of the project. So that means that we're basically now focusing on this part of the project, TRL6. So many of the demonstration is happening at the company sites, and the integration of the alternative energy forms is happening at this moment. I'll briefly give you a couple of results. I won't go much into the details. There's no time for that, but I just want to share with you some of the work that we've done. Let's move first to the polyurethane in the reactive extrusion. Again, this is the Coatex case, where Coatex and many of the partners are working on these reactive extruders. And you see here a picture of a pilot extrusion line of 18 millimeters diameter. There's also another one that is being investigated in the project that's a 27 millimeters extrusion line. So these are already large installations on the level of pilots. And obviously we've been, as I said, we've been first looking at the transition of a batch process, because this was really a batch process, moving to a continuous flow process in these extruders. So that meant that we had to look at dosing, we had to look at safety, at encapsulation, we had to look at the process control system of the continuous system. That is now all demonstrated, all underway or being finalized, and we can now move to the addition of ultrasound and microwave. And also there, based on the more laboratory level work, we're now integrating ultrasound and microwave into the extruder. And you see here a schematic of the extruder, which is shown here. Feed streams are coming in at the left side. Polymerization is happening over the extruder length, and in the end, the finalized, the formulated polyurethane is reached or is collected. And as you can see, microwaves is mostly being applied in the beginning of the system for heating up all the different feed streams. Ultrasound is also being applied, but can be applied along the length of the extruder. The extruder is modular based, so that means that, and you can see that slightly here, you have individual modules being put together, and so we can actually choose which module we're going to irradiate, either with microwaves or with ultrasound. The integration has required some building of new pieces, new devices, new sonotrodes, new devices for the microwaves. You see here the microwave block that needed to be adapted with quartz windows. You see here the sonotrode that needed to be adapted also to the twin screw system that we have in place. For the zeolites, we first started with the transition to flow, and we demonstrated, or we validated the continuous oscillatory baffle flow reactor. You see it here. This is a large installation. You have here the continuous system. This is a 40-meter length continuous flow reactor with baffles in side of the tube, which allows, and then with pulsing operation, which allows to have this oscillatory baffle flow. So large-scale operation, we've have quite some very interesting results, but we're also looking at a more fundamental perspective. We're looking at, for example, the fluid dynamics within the COBR, both by modeling, as you can see here, but also with experiments. For example, this is a picture from a PIV experiment and particle injection velocimetry system, where we're actually having solids in the liquid, and we can follow the trajectory of the solids while doing the pulsation in this OBR configuration. And so, as I mentioned before, we're now also integrating ultrasound and microwave at different locations in the system. We can have, for example, microwaves present for heating of the different feed materials, but also along the COBR. We can also have ultrasound in the mixing phase, and again also within the COBR for nucleation enhancement of the zeolite nuclei, or also of deagglomeration of the formed products. A picture that shows a little bit how this is integrated. So here you see the bends of the COBR. We're actually putting, or we're able to put the sonotrode at the bends. This is at the beginning of the COBR, where we're using the ultrasound probe for reaction kinetics enhancement. More towards the end of the reactor, we're basically using ultrasound for deagglomeration. And the same holds for microwaves. We were a bit delayed there, also due to materials that were not arriving due to COVID pandemic, but we're also now have everything in place to perform the experiments there, to perform the microwaves or use the microwaves in the COBR as well. And then the last use case is the nanotitania in the plug flow reactor. That's with Colorobia. This is also a batch process at the moment. We've investigated both ultrasound and microwaves. So we've seen that ultrasound is not really the most relevant technology there. So we've continued with microwave heated plug flow reactors. And basically, this is the process that we've been investigating, or one of the processes within the nanotitania synthesis, which is the first stage of the process. So the precursor is being mixed with reactants, heated for the synthesis, then distillation of some liquids that we are not that we want to recuperate, and then in the end we have a colloidal suspension with the required concentration. A picture of the microwave installation. We've done a lot of work on building the right geometry, or understanding the right geometry needed for the plug flow reactor. Basically, the plug flow reactor is a straight tube inside the microwave cavity. And of course, the work on the microwave cavity has been such that we're trying to enable a uniform distribution of the microwaves along the tubular reactor. We're now in the stage of assessing the techno-economics and the life cycle of the developed processes. I can give you some very rough indications for the polyurethane in the reactive extrusion. For example, we see that we have a large reduction in carbon footprint, and therefore because of the reduction in energy requirement from gate to gate. Large meaning in the order of more than 70%. Slightly less reduction, or less reduction in the carbon footprint if you calculate from cradle to gate, then we're in the order of 10 to 20%. Zeolites in the COBR, there we have somewhat lower reduction in the energy consumption, which is possibly not outweighing the higher material intensity that is needed. Although here in this case, the deagglomeration by ultrasound, for example, is not yet taken into account, which will have an effect on the downstream processing, as was already also mentioned. And this is important to take into account, which is already mentioned by the other projects as well. In the nanotitania case, we only see a small reduction in the carbon footprint, but only one stage in the process has been studied. Calcination of the titania has not yet been studied, or is being studied at this moment, but not yet from an LCA perspective, and we expect there better improvements. The Simplify project is a project that went from TRL 4 to 6, and we're now arriving at TRL 6. And we've been able to secure a follow-up project, which is the Simply Demo project, which works further on two of the case studies that we had in Simplify, the Coatex case, the polyurethane case, and the Arkema, the zeolite case. and we're also combining that with 2 other polymerization and crystallization cases from other partners, and that has recently started this year, and that's another project for 4 years. And as you can see there, we're aiming at a higher TRL level, TRL 7. Okay, so that is the end of my presentation, and I want to thank the organizers, I want to thank the audience, and you can see also here my email address and also the website of our project if you're interested to find out more about Simplify. Thank you very much.
Yes, thanks to you, Tom, for presenting the Simplify findings so far. We've now concluded the presentations from each project. I do not see any questions in the chat, but maybe the representatives from the projects have some comments about the other projects. So maybe, Tom, you have some thoughts about the other projects. Or maybe Evelina, you want to say something about what we've heard so far? I don't want to put anyone on the spot here, but maybe there are some questions or comments apart from the chat. I think everyone who presented can, if they want to unmute themselves and ask questions or comment. Otherwise, I'm waiting if maybe a question pops up in the chat. It's also a good sign. So you presented in a way that there were no questions left. Everybody has a very good impression of the projects and what has been done so far. And maybe it's just anxious to get into personal contact via email or check out the individual project websites, which might be a good sign as well. Okay, so I don't see any questions and I don't hear any questions, which let's say it's a good sign because you presented in a very comprehensive way. Thank you to everyone who presented today. So Tom, Angel, Erwin, and Evelina, thank you for your talks and presentations. And also thank you to Icons and the Horizon Results Booster team who helped us organizing this event. They've also recorded this session, and the link to the recording of the presentation will be sent to our participants. We will also post it on our website, so you can take a look at it afterwards if you want to look again at the presentation you've seen before. If you're interested in additional details, additional input about the individual projects, don't hesitate to contact the representatives of the projects themselves. We're happy to share, spread the word about our projects and the innovation that is currently being developed. So that leaves me to say thank you to everyone involved and have a good rest of your day.
Thank you. Bye-bye.
Bye.
Okay, thank you.
Thank you. Bye.
Bye.